Hey, welcome back to my Introduction to Mathematical Proofs playlist. Today we'll be talking about sets. Okay, so sets are one of the most fundamental objects in math, and we need to understand what they are. And in actuality, the definition is quite simple. They're just an unordered collection of unique objects. Like, that's literally it, right? So when we're talking about notation, we usually use capital letters to denote sets. So in this case, we let A is equal to, and then in this case, we write out exactly what elements are in the set. So in this case, what we write out here, A is equal to, and then you have the brackets, 1, 2, 3. It's a set containing elements 1, 2, and 3. And we use the word element on purpose, right? So 1 is an element of A or is in A, but 4 is not an element of A. But it's an unordered collection of unique objects. It doesn't necessarily have to be numbers, right? So for example, B is equal to cat, dog, buffalo is also a set. And the elements in B are cat and dog and buffalo. Now, whether we're actually talking about the word itself or like an actual cat, actual dog, actual buffalo, depends on the context, right? So, for example, if we have a set Z that represents maybe all the different animals at the zoo, it makes sense to talk about, oh, these are the actual animals we're talking about, right? But if we're talking about a database of words, maybe a dictionary, then we're talking about the words themselves, right? So, what they actually are is context dependent as well. All of this is to pretty much say that a set is very broad, but in our context, we only care about numbers. So let's look at just a few more examples, right? C is equal to 2, 5, 7. This is a set which has three elements, the numbers 2, 5, and 7. You'll notice D here has 10, 17, and 10, but these are not unique objects. Two of them are duplicates, so this actually isn't a set. And A here, it has, well, yeah, so it has 3.5, that's fine, but it's unordered. But once again, the order doesn't really matter, so this is still a set. And notice how we reuse the letter A. Once again, it's like how we always reuse the letter X in algebra. Everything is context dependent. There's a few questions we might have about sets, right? Maybe the first thing we want to ask is why are they useful, right? Well, the reason why is because they're really abstract, right? They can literally contain whatever we want. So we can abstract our math as much as we, for our purposes, which is more important, it provides definition and rigor to what we're doing. Remember, what we're trying to do is find a systemic way to think about math, right? Okay, here's this. This is true. This is a definition. How can I go from going from a definition to proving something else? And having a definition to work with is very, very helpful because it allows us to build more things. For example, how would you answer the question, what are numbers, right? There are many different levels to this different question, and explaining it would be kind of hard, but it's actually really easy with the language of sets. And we'll literally talk about this next episode. Not to mention that functions formally literally can't be explained without sets. And this is one of the most simple structures we'll study in math that comes up everywhere, right? So sets are very fundamental. There's many ways that we can define these sets, but the idea is we need to think of writing sets more compactly or writing infinite sets. You will notice before we use curly brackets, but here's another way we can define a set. If we let A is equal to 0, 1, but with round brackets, this is the open interval from 0 to 1. So this contains every number between 0 and 1, not 0 and 1. So 0.5 is in here, pi over 4 is in here, but 1 is not in there and 0 is not in there. And we can also have closed intervals. So closed intervals use square brackets, and these include the endpoints. That's what we call the numbers, the endpoints. So in D, 1 is in there and 0 is in there. And we can also have half open sets. So maybe one side's an open bracket and one side's a square bracket. So let's say E is equal to open bracket 0 comma 1 closed bracket, then 0 is not in E, but 1 would be. And we can also extend this to infinity. So it can be 0 comma infinity. But since infinity is not a number, we don't include it, so we always put a circle bracket at the end there. But then there's also another way we can define sets, and this is called set builder notation. So let's look at the set B. So B is equal to the set X such that X is greater than 3 and X is even. So pretty much the sets are defined in a specific way. The first thing that we have is the form of the elements in the set. So in this case, it's just X, and X is just a number. Then we have a colon or a line separating it from the conditions that we have. If the numbers meet the conditions to the right of the colon or the line, then it's in our set, and otherwise it's not. So in this case, we know that 4 is in our set B because 4 is greater than 3 and even, but 2 is not because 2 is not greater than 3. And you might have noticed I use this kind of weird symbol, the E looking thing. E means in, and the E with a line through it means that it's not in there. And you can also see that 5 is not in here. And what's interesting here is we use the word and X is even. We're literally using English, right? But we're using English because it's precise. There's no other way to interpret what it means for a number to be even or what the word and means. So it's okay to use English in set builder as long as it's very clear. So in essence, sets are actually the first tools that we have to understand math. So one really interesting thing, another interesting property, is that we can have sets within sets. Let's take a look at this example right here. If we have A is equal to the set containing 1 and 2, it's perfectly fine for B to be a set that contains A, 4, and 5. So yes, B is a set that contains another set as an element. It's really weird, but a way that you can think about it is if B is a really, really big box, then inside A you can have like a smaller box that contains other things, right? And here's the thing, 1 is not actually an element of B. So it's very interesting. Keep in mind, B only has 3 elements in this case, right? There's the set A, 4, and 5. So the set 1, comma 2 is in B, but 1 itself is not in B. So this is something we need to be careful of when we're working with sets inside other sets. But how else can we talk about relationship between sets, right? So we might have sets in another set, but what if we want to describe a relationship where all the elements in A are also in B, right? Then we see that A is a subset of B. So in this example, A is equal to the set containing 1 and 2, and B is the set containing 1, 2, and 3. Since 1 is in B and 2 is in B, all the elements in A are in B, so A is a subset of B. And we denote it with this symbol right here that kind of looks like a U with a line under, sideways U with a line underneath it. And this is saying that A is a subset of B. But now, what if we change A to be 1, 2, and 4? Well, since 4 is not in B, A is not a subset of B, so we just put a line through all of it. Okay, so now the question is, why would we even want this definition? Why is this useful, right? Subsets are important because they indicate some sort of relationship between a set, right? But here's also something just as important. What if two sets are equal, right? What if we have two different representations for the same set? How do we actually prove that they're equal? And we'll answer this soon, but we'll need a few more tools before we can answer that. So a question we might have is, what can we do with sets, right? Is there any ways that we can combine them or manipulate them with respect to one another to achieve a goal? For example, if we have, let's say, a set of English words and another set of easy English words, what different ways can we combine them? Maybe a way that you can combine them is making a list of non-easy or hard English words by removing all the easy words. So you have two sets and you're manipulating them in such a way to get something else, right? Or let's take for another example, set A representing one zoo's animals, okay? And another set B representing a second zoo's animals. What ways can we combine these sets? Maybe all the animals in both zoos. So if I visit zoo 1 and zoo 2, what are all the animals I can see? Or maybe regardless of whether I go to zoo 1 or zoo 2, and I can only go to one zoo, what animals am I guaranteed to see, right? So be careful, there's a lot of definitions inbound, but these should make sense. And with a little bit of practice, you'll be fine. So the first way we can talk about this is intersection, okay? So generally, if A and B is any two sets, we define the intersection with this kind of n-looking thing as all the elements that are in X and also in B. So here we use set builder, all the elements of form X, where X is in A and X is in B. So for example, we'll just use the same example for everything. C is equal to 1, 5, and 9, and D is equal to 5, 6, and 8. We'll notice that the only things they have in common is 5. So the intersection of two sets produce the elements that they share, or the elements that are in both sets. Likewise, we have the union. In union, we use the word or instead of and, okay? So in the set builder, X, so all the elements X of the form where X is in A or X is in B. So what this will do is this will produce the combined elements or the elements in both sets. Okay, let's look at difference, right? So A remove B or A difference B is all the elements of the form where X is in A. So our elements are from A, but they're also not in B. So in this case, we'll notice that since 5 is in B, C difference D or C remove D is 1, 9. The difference of two sets produces the elements that are in one set and not in the other. And we'll notice if we do D difference C or D remove C, we're going to get a different set here. Okay, this one's a little more complicated. This is called a complement. So imagine a set that has everything we want, or all the elements that we want to consider, and we're going to call this the universal set. So usually U will be the set of all numbers, but in this case, we'll just let it be all the positive non-decimal numbers. Then we're going to have a complement of a set. So in this case, a complement will be all the values of X that are in the universal set and not in our set. Or alternatively, it's the universal set remove or set difference or difference A. So let's just look at the example. D complement is 1, 2, 3, 4, 7, 9, 10, 11, 12, 13, and so on. We remove the elements that are in D. So the idea here is the complement of a set produces all the elements not in our original set. So we're going to get everything that's not in our set. And of course, everything depends on the scale that we're looking at. It depends on the universal set. So in this case, since we let your universal set, or everything we want to consider, be all possible positive non-decimal numbers, that's why we get 1, 2, 3, 4, 7, 9. But if we had it be every single number from negative infinity to infinity, then we'd have to represent it as a union because we're removing specific. And the fifth operation is a little complicated. It's called the Cartesian product. And we denote this with this little cross here, A times B. And it produces a new set, but the sets are pairs of elements. So they're going to be of the form x comma y, where x is from A and y is from B. So we literally produce pairs of elements. And once again, the form is of x comma y, so that's why all the elements in our set are going to be something comma something. And the easiest example where you've seen something like this is the Cartesian plane or the 2D plane, the grid, right? It contains all pairs or all xy values. So 1 comma 2 is there, 3 comma 1. And if I tell you to graph it, you'd be like, oh, it's here, oh, it's there, right? In this case, we'll have a finite amount of pairs. So 1, 5, 1, 6, 1, 8, 5, 5, and so on until 9, 8. So a Cartesian product of two sets produces all the pairs of elements, or all possible pairs of elements, where the first index, or the first number, comes from A, and the second index, or the second number, comes from B. It's just memorization, which is a little annoying, but these definitions come up often enough. Don't worry, you'll just need a little practice with them. So we talked a little bit about set equality, but we'll actually talk about it. What does it mean to have two sets that are equal? We say that two sets are equal when they actually contain the same elements. So they represent the same unordered collection of unique objects. So for example, if A is all the positive odd numbers and B is all the positive even numbers, prove that every positive non-decimal number is A union B. We use this weird n to denote the set of all positive non-decimal numbers. How do we show that A union B is equal to n? Or how do we show that they're actually the same thing, just different representations of it? Well, the idea is this. If we can show that A union B is a subset of n, by definition, every positive, odd, and even number is, well, a positive non-decimal number. And if we show that n is a subset of A union B, by definition, we have that every non-positive decimal number is either odd or even. Okay, so these are two different things. But when we combine them together, this shows that every element in n is also an A union B, and every element in A union B is also an n, so they're actually the same thing. So what we do here is we show that n is a subset of A union B, and show that A union B is a subset of n. And by doing so, we get that they're equal. And we call this a double subset inclusion. And this proves that the sets are actually equal. And this is really interesting. So remember how in our symbol we use the little sideways U with a line underneath? The line is saying that, okay, it can also be equal to the set. So if x is less than or equal to y, and x is also greater than or equal to y, then they're equal, right? So that's another way you can think about double subset inclusions. So this proof is actually pretty simple since we use like obvious facts. It's not really rigorous, right? So let's just run through this. This proof is pretty simple since we use like obvious facts, and it's not really rigorous, but we'll just start by doing it. So the first thing we show is that n is a subset of A union B. So we'll just take a random positive non-decimal. If n's odd, then it's an A. If it's even, then it's in B. So it must be in A union B. So we must have that n is a subset of A union B. Now we'll show the other direction. A union B is a subset of n. Well, take an arbitrary element in A. Well, since x is positive and clearly a non-decimal number, since it's odd, we must have that x is an n. And similarly, if x is in B, x is also a non-decimal positive number because it's even. So x is an n. So every element in X union B is a subset of n, or is in n. Thus, A union B is a subset of n. And now that we've proven both subset inclusions, we must have that A union B is equal to n. And there's just one little caveat that we actually need to think about, okay? So how do we describe a set with no elements? We use this weird symbol right here. It's a circle with a line going through it. And this is called a null set. So a null set is a set that doesn't contain anything. How do we literally represent a set that doesn't contain anything? Well, A is equal to the null set. To say that A is an empty set. So we say that every set is a superset of the null set, or that the null set is a subset of A for all sets. I use the word superset. So the idea here is that, okay, we have that, let's say A is a subset of B. Well, what's the opposite direction? B is a superset of A. Is the bigger set in a sense, right? But the idea here is that the null set is a subset of every single set. Think about it. If a set doesn't have any elements, how are we going to show that every element in there is also in another set? We can't. So it's true just because, well, there's no way to disprove it. And this is called vacuously true. This doesn't really come up often, both the word vacuous and the null set, but it's always something we need to consider when we're making a claim about sets, because sometimes the only counterexample we can come up with is the null set. So that's why it's something to be careful of. So the null set's a set without any elements. And here's kind of the worst part about it, right? If we let A be a set containing the null set, I know this is really confusing. The idea here is A is a set, and the only element in the set is a set that has nothing in it. So A is a set containing the null set as an element. I think you can see why this is really bad. And then we have B is equal to A for 5. And then the null set is actually a subset of B, but the set containing the null set is in B. Do you see why this is confusing? Because we can have sets within sets. So we can have the null set be within another set, but then it's also a set, and it gets kind of confusing, right? So A is a set that contains the null set as an element. And then, because of the way we define B, the null set is a subset of B, but then the set containing the null set is also in B. Yeah, that's pretty bad. This doesn't make sense. Don't worry about it too much. So that was a lot. There was a lot, right? So here's just a quick cheat sheet of definitions and just how to build sets, right? So playing around with all these definitions and seeing how examples work help us understand better how the sets work. Generally, we won't need too much advanced machinery. You just use definitions to work on this. Once again, we're developing literally the broadest tools to understand mathematics, right? The idea is all of this will help us solve problems down the line. And as always, there are links below to help out and find some worksheets, since this is pretty annoying to work with. And they'll help you get used to the definition. Okay, I'll see you soon.